Grounding system evaluation is crucial to ensure adequacy and proper installation, as poor grounding contributes to stray ground currents. Soil conditions, specifically conductivity and moisture content, significantly affect ground current flow. Low conductivity soils may not support significant ground current. Current balance on the distribution line is essential. Phase currents should be balanced to minimize neutral currents, as unbalanced currents increase stray ground currents. Equipment grounding must be verified to ensure that all electrical equipment, including well pumps, is properly grounded. Poor grounding creates paths for stray ground currents. Lightning protection measures are needed since lightning strikes can induce ground currents. Adequate lightning protection should minimize stray ground currents caused by lightning. While using delta-configured transformers can reduce ground currents, it introduces additional considerations. Firstly, overvoltage protectors for the secondary neutral add to the cost. Secondly, delta transformers exhibit poorer voltage regulation than Y transformers, potentially leading to voltage fluctuations in the distribution system. Thirdly, delta transformers can introduce harmonic distortions into the power system, affecting sensitive electronic equipment. Fourthly, delta transformers typically require more frequent maintenance than Y transformers. As alternatives, improved grounding can enhance the grounding of the distribution system and individual homes to reduce stray ground currents. The use of isolating transformers can isolate individual homes or well systems from the distribution system. Capacitive compensation involves installing capacitors on the distribution line to reduce neutral currents. Current balance devices can be used on the distribution line to reduce phase current imbalances. A thorough evaluation of the distribution system, soil conditions, and electrical equipment grounding is recommended to identify the source of stray ground currents. Exploring alternative solutions, such as improved grounding or isolating transformers, before implementing a widespread switch to delta-configured transformers is also recommended. Consulting with a qualified electrical engineer or utility representative is essential to determine the most appropriate solution. The National Electrical Code, 2008 edition, provides relevant guidelines for grounding and wiring practices. Section 250.4 A5 covers grounding of electrical systems and equipment, ensuring a low impedance path for fault currents. Section 250.24 addresses grounding requirements for separately derived systems. Section 250.50 discusses grounding electrode systems, including grounding rods and their installation. Section 300.3 B outlines the requirements for grounding conductors. Section 310.15 pertains to ampacity of conductors, including neutral conductors and Y systems, which can be affected by unbalanced loads. Section 314.4 provides guidelines for bonding metal enclosures to ensure electrical continuity and grounding. Section 408.41 covers grounding of panel boards and switchboards. Section 547.9 addresses grounding requirements for agricultural buildings, where stray voltage can be a concern. Section 690.47 pertains to grounding of photovoltaic systems, ensuring proper grounding for renewable energy sources. Grounding electrode conductors must be sized according to NEC Table 250.66, based on the size of the service entrance conductors. The minimum size for a grounding electrode conductor connected to a ground rod is typically no smaller than 6 AWG copper. The grounding electrode system should have a resistance to ground of 25 ohms or less, as per NEC 250.53. A2. If the resistance exceeds 25 ohms, an additional grounding electrode is required. The neutral conductor in a Y system carries unbalanced current, which can contribute to ground current if not properly managed. Delta systems, on the other hand, do not have a neutral conductor and therefore do not carry unbalanced current in the same way. However, delta systems can still have ground currents due to capacitive coupling and other factors. The overvoltage protection device used with a delta transformer should be rated to handle the maximum voltage that could occur during a fault condition. This device should also be able to quickly interrupt the fault current to prevent damage to equipment.
The location of grounding electrodes should be carefully selected to ensure good contact with the earth and to minimize the risk of corrosion. The round rod should be driven deep enough to reach permanent moisture, typically at least 8 feet. The spacing between grounding electrodes should be at least 6 feet to minimize interaction between their zones of influence. The use of ground-enhancing materials can improve the conductivity of the soil around the grounding electrodes. Regular inspection and testing of the grounding system are essential to ensure that it remains effective. This includes checking the resistance of the grounding electrode system and inspecting the condition of grounding conductors and connections. Stray voltage can be caused by a variety of factors, including improper grounding, unbalanced loads, and inductive coupling. It is important to identify the source of stray voltage before attempting to mitigate it. Mitigation techniques for stray voltage include improving grounding, balancing loads, and using isolating transformers. The use of shielded cables can also help to reduce inductive coupling and stray voltage. In some cases, it may be necessary to install specialized equipment to mitigate stray voltage. This equipment may include filters, reactors, or other devices. The cost of mitigating stray voltage can vary depending on the severity of the problem and the mitigation techniques used. It is important to carefully evaluate the costs and benefits of different mitigation techniques before making a decision. In rural areas, stray voltage can be a particular concern due to the long distances involved in the presence of livestock. Stray voltage can cause livestock to exhibit a variety of symptoms, including decreased milk production, reduced weight gain, and increased susceptibility to disease. It is important to take steps to mitigate stray voltage in rural areas to protect livestock and ensure their well-being. The National Rural Electric Cooperative Association provides information and resources on stray voltage mitigation. The Rural Utility Service also provides funding for projects to improve the reliability and safety of rural electric systems. The Institute of Electrical and Electronics Engineers develops standards for electrical equipment and systems, including standards for grounding and stray voltage mitigation. IEE Standard 142 provides recommendations for grounding of industrial and commercial power systems. IEE Standard 519 provides recommendations for harmonic control in electrical power systems. IEE Standard 1100 provides recommendations for powering and grounding sensitive electronic equipment. The National Fire Protection Association publishes the National Electrical Code, which provides requirements for safe electrical installations. The National Electrical Safety Code provides requirements for the safe operation of electric power systems. Proper grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protective devices to operate and clear the fault. Bonding connects metal parts of the electrical system together to create a low-impedance path for fault current. The use of ground fault circuit interrupters can provide additional protection against electric shock. GFCIs detect ground faults and quickly interrupt the circuit, preventing serious injury or death. SIs detect arc faults and quickly interrupt the circuit, preventing electrical fires. Surge protective devices can protect sensitive electronic equipment from voltage surges caused by lightning or other events. SPD should be installed at the service entrance and at individual equipment locations. Regular maintenance of electrical equipment is essential for safety and reliability. This includes inspecting wiring, connections, and overcurrent protective devices. Damaged or worn equipment should be repaired or replaced promptly. Electrical work should only be performed by qualified electricians. Unqualified individuals should not attempt to perform electrical work, as this can be dangerous and can violate electrical codes. Electrical permits are required for many types of electrical work. Check with your local building department to determine if a permit is required for your project. Electrical inspections are conducted to ensure that electrical work is performed in accordance with electrical codes. A delta high leg configuration can introduce additional harmonics and grounding considerations. This requires careful planning and execution to ensure safe and reliable operation. The high leg voltage to ground is approximately 1.732 times the phase voltage. This higher voltage poses a potential hazard and must be clearly identified. The high leg is typically marked with orange tape or paint. The high leg should not be used for lighting or small appliance circuits. It is typically used for three-phase motor loads. The grounding of a delta high leg system is typically accomplished by grounding one phase of the delta winding. This creates a grounded corner delta system. The grounded phase is typically the center tap of one of the delta windings. The grounded phase must be identified and marked. The grounded phase conductor is typically white or gray. The size of the grounding electrode conductor for a delta high leg system must be sized according to NEC Table 250.66. The grounding electrode conductor must be connected to a grounding electrode system that meets the requirements of NEC 250.50. The grounding electrode system must have a resistance to ground of 25 ohms or less. If the resistance to ground exceeds 25 ohms, an additional grounding electrode is required. The use of a ground fault circuit interrupter is recommended for all circuits in a delta high leg system. GFCIs provide protection against electric shock by detecting ground faults and quickly interrupting the circuit. Surge protective devices are recommended for delta high leg systems to protect sensitive electronic equipment from voltage surges. The surge protective devices should be installed at the service entrance and at individual equipment locations. Regular maintenance of the delta high leg system is essential to ensure safe and reliable operation. This includes inspecting wiring, connections, and overcurrent protective devices. Damaged or worn equipment should be repaired or replaced promptly. Electrical work on a delta high leg system should only be performed by qualified electricians. Unqualified individuals should not attempt to perform electrical work, as this can be dangerous and can violate electrical codes. Electrical permits are required for many types of electrical work on delta high leg systems. Check with your local building department to determine if a permit is required for your project. Electrical inspections are conducted to ensure that electrical work on delta high leg systems is performed in accordance with electrical codes. The NEC 2008 provides specific requirements for delta high leg systems in Article 455 covering phase converters and Article 408 pertaining to switchboards and panel boards. Additionally, Article 250 contains comprehensive grounding and bonding requirements.